Welcome back, everyone, and thank you everyone for joining to the last two sessions. And in the last tutorial, we will be hearing by Jay Kalinani. Jay Kalinani is a postdoctoral researcher at University of Illinois at Urbana campaign, and he will be giving a tutorial on AsterX. And he is actively contributing into the many parts of the Einstein Toolkit, and he will be giving the tutorial on AsterX. Thank you, Jay. You can.
Oh, thank you, Behan, for your very kind words. And I thank the organizers, first of all, for giving me this opportunity to speak, and also Steve for helping me set up the tutorial notebooks. So this I will try to do this in two parts. The first part, I will try to give you some overview about AsterX. And the second half, we have some notebooks that we can check and try to do some simulations. Before, if a prerequisite that you might need is to actually compile the Cactus, the build setup. So if you haven't already, we'll just quickly show you that you need to log in here. And if what you need to do is run this Cactus tutorial if you haven't already. And in here, you would have to essentially run this build and untar this Cactus tarball. And
Jay,
yeah, run these.
Jay, all
Yes.
all they'd have to do is run the untar. That's it.
Yeah,
There's
that's
nothing
correct.
else.
Exactly. So you nothing else. That's exactly. So if you haven't already done that on day one, please kindly follow through. And please feel free to interrupt me at any point. I sometimes might not see what's in the chat, so just unmute yourself. I think the Steve also mentioned that there is this the code to log in for the tutorial in the chat, so please feel free. All right, so in the meantime, in case you haven't done it already, you can probably already start this in the background while I can introduce some slides on AsterX. Right, so the AsterX is essentially a new GPU-accelerated GRMHD code for dynamical spacetimes, and GRMHD stands for General Relativistic Magnetohydrodynamics. And this is, of course, a collaborative effort. It's not. It's been done with efforts from a lot of people. Especially the main developers are Li Weiji, Mikhail Shabanov, Lorenzo Noggi, Alan Wen, and the other also contributors like Federico Armengol, Lucas, Johnny Stau, and then of course Steve, Manuela, Ricardo, Bruno Giacomazzo, Roland, Eric Schneider, as well as Joseph. We also have a paper out on AsterX, and here is the link to archive. And yeah, if you have any questions also in the future, please feel free to contact me on my email here. Right, so why do we care about GRMHD? So in case we want to study different astrophysical processes around compact objects, and that's where the G comes in the picture. And if you want to study the hydrodynamics part, for example, in proto-neutron stars or on binary neutron star mergers, or even study gas dynamics across around supermassive binary black holes, or even understand some of the physical processes for magnetic fields like amplification mechanisms like magnetorotational instability, or jets from either a magnetar or a oracle. We definitely need such simulations. And then why do we care about GPUs? So if you check, most of the fastest supercomputers now, at least top 9 out of 10, are based on these GPU accelerators. And there has been a strong shift in the past five years or so to use GPUs because we can make computations really fast. Now, you may have already heard a bit about GRMHD from the talk of Professor Philip Mosta But just to give you a very quick recap of what everything entails in GRMHD, the kind of variables you're trying to solve or evolve are called conserved variables. And based on that, the actual physical variables that you care about are these primitive variables. So primitive variables in the sense of rest mass density, velocity, especially in energy, and sometimes you might also need electron fraction, which is essentially a ratio of number of electrons to number of baryons. And based on these primitives, you define these conserved, what we call conserved variables, and these are conserved density, momenta, internal energy. Also, you have magnetic fields, densitized one, as well as electron fraction. And any GRMHD code typically includes this kind of equation that you want to solve. And this is essentially a first order flux conservative hyperbolic equation, which is also is essentially in Valencia formulation. And here, alpha is your lapse, gamma is your the spatial metric trace, and you have u as your state vector. That's the variable you're trying to evolve in time. And then you have the fluxes that you compute at the cell interfaces. And then you have your source terms. So all of these equations are essentially conservative equations in the sense that, for example, the first one is essentially a conservation of mass equation. The second one is conservation of momenta. Third one is conservation of energy. And then the fourth one is essentially how you evolve your magnetic field. And the last one is how you evolve your electron fraction. And when you have non-negligible source terms or the right-hand sides, that means you are, for example, it comes through the T mu nu, and which essentially means you can interchange energy and momenta with the space-time itself. And this is how your T mu nu typically looks like. Now, to close these system of equations, you also need what we call as an equation of state. So there are different varieties of equation of state available in the market, depending also what kind of problem you want to solve. For example, if you want to model the gas and the dynamics around the black holes, an ideal gas equation of state might work perfectly fine. But then if you want to model neutron stars, then there are different equations of state in terms of like hybrid equation of state, have a piecewise polytrope plus thermal component, or you can have even these what we call three-parameter equation of state, which you have pressure in terms of density, temperature, YE. Lastly, to be able to for this flux conservative formulation, there's something called as high resolution shock capturing schemes. So when you're trying to evolve, you start with some initial data, you start evolving, you might develop shocks during the evolution, and to capture these shocks or to resolve these shocks well, there are different approaches. So for this, so to make sure that you're capturing these the details well. Uh, Codes typically involve a two-step process. One is a reconstruction. So whatever variable that you have probably at your cell center, you want to reconstruct them at the cell faces. And then you apply what we call as approximate Riemann solvers, where you generate a shock condition at a Riemann problem at the cell interface, and then you try to solve these using these Riemann solvers. Another important ingredient in these GRMHD codes is something called as a contour-prim solver. So currently there exists no analytical system. As I mentioned earlier, there are these analytical prescriptions for computing conserved variables from the primitive variables, but the other way around is it's not, we don't have any analytical solution to compute the primitive variables once we evolve the conserved variables and you want to retrieve those primitive variables. So we have to jump to root finding algorithms, and these are called conservative to primitive or con to prim or C to P algorithms. And there are different C2P algorithms proposed in literature, and they typically are based on two different kinds of methods or schemes. One is like the Newton-Raphson root finding techniques. They typically start with an unbounded root, and you need to provide an initial guess. And these schemes might depend also on your equation of state derivatives. The second kind are root bracketing schemes, where you know that, okay, your root is going to be bounded in a certain regime, and they might not depend on an initial guess and on the US derivatives. So Newton-Raphson schemes are typically faster, but might be not as accurate, or while root bracket schemes are slower, but they might be a bit more robust or accurate. So to give you a quick understanding of the code workflow. So again, the reminder, this is the kind of first order hyperbolic equation you're trying to solve. So you start with some initial data, and you define your primitive variables at each grid point in your simulation. And then the first thing you do is prim to con. You can compute the conserved variables at iteration 0. And then once you have your conserved variables, you can also compute your source terms using some finite differencing schemes. Then you use these high resolution shock capturing techniques to compute the fluxes at your self interfaces, essentially employing these reconstruction plus Riemann solvers. And then finally, once you have the flux minus source, gives you kind of like an ODE that you can then uh, solve using a integrator such as an RK4 method. And finally, once you've done all of this, you can get back your primitives for the next time step using this conservative to primitive technique. And then you keep looping this you keep iterating until you reach the end of your simulation or your problem that you want to solve. Now, jumping to what we have here today, AsterX is the underlying software infrastructure that's been developed for massively parallel block structure AMR.
Jay,
yes?
There is a question in the chat. Robin asks, what about the equation of state? Do you depend on an other term for that?
Oh, that's a good question. I'm coming into it in a couple of slides. So that was just to give you an understanding of that, like we need an equation of state, and then I will just show you what equation of states we have, or the term we have for that. Right. Right. So based on AsterX is the new driver for the Einstein Toolkit, CarpetX, and this is spearheaded by Eric Schneider, Roland Haas, Steve Brandt et al. And through CarpetX, there is support provided for GPUs. Also, we have this dynamical block structured AMR that one can use. And of course, it also has facilities for flux registers that allows for hydro-refluxing. And all of this development is open source. So if you check out this link, you'll be able to get to the GitHub repository of CarpetX. And CarpetX has already seen a few applications. For example, there's this open source code called CanudaX, which essentially currently solves the Einstein field equations in vacuum. And this is led by Chen Xing at University of Illinois Urbana-Champaign, along with Tech et al. And on the right is what you see is Cheng Xing had performed this binary black hole merger simulation, and here you see the evolution of Psi4 and how you can dynamically also refine or de-refine your grid during the in-spiral and then after also doing merger. Let me also mention that there is definitely another GRMHD code called GRMX that has also been developed, and this has been led by Swapnil Shankar, Philip Masta et al. And similarly, we have our new code called AsterX, and Aster essentially means, in Greek, it means star, and in English, it essentially is a genus for plants that have flowers which look like stars. So that's how the symbol comes from, and X stands for exascale. Now, AsterX has been heavily adapted from the code called Spritz, and which was the carpet based. So we've taken a lot of numerical algorithms from there, but AsterX has been written completely from scratch. in our favorite language, C++. People might disagree on that. But we have tried to keep its design very modular. So you have different torrents for each of the codes, and that's the schemes that we've implemented. For example, there is a torrent called ReconX, which has different reconstruction schemes like minmod, piecewise parabolic method, PPM, VNO-Z, as well as MP5. Then we have flux solvers like Lax-Frederick flux solver as well as HLLE. Then for ContoPrim, we again have this module called, or torrent called ContoPrim Factory, which has a few different ContoPrims, such as the 2D method of Noble et al., the 1D method of Valenzuela, as well as we recently also added the 1D method of Castan et al. Called Reprimand. This is and ported it to GPUs as well, and this is currently under testing, and there is also backup, entropy backup as well. Now, AsterX also solves, instead of magnetic field, evolves the vector potential. And the plus point of using CarpetX is that it allows for staggering of these different variables. For example, you can have cell-centered, vertex-centered, face-centered, as well as edge-centered variables. So you can store them in these different locations. And for example, when we are trying to evolve the vector potential, a good way to include the vector potential is to store the vector potential variables on the edges. This way, when you take the curl of A, you get B directly on the cell face, and that's where you want that. And this allows for the divergence of B also to by construction will remain zero, and so this is a plus point of using CarpetX. Next, I think there was a question about EOS. So there is a module called EOSX, which provides different analytical equations of state, such as ideal gas or a simple polytrope. There is a hybrid support for hybrid equation of state as well. It's currently under testing. And then there is we've added support for finite temperature tabulated equation of state. And as I mentioned earlier, we evolve the vector potential. We do evolution of vector potential instead of the magnetic field directly. Another thing that GRMHD simulations suffer from is that you cannot have an exact vacuum in the code. So you typically add what we call as an atmosphere or a floor. So this would employ like some kind of density or pressure and temperature as a background. And what happens is currently, until now, most of the codes have included such background where they impose like a static constant density, constant pressure and temperature floor throughout. So what we've included now is a grading, which means that as you move away from the source and go away in the domain, you can have lower densities and pressure and things like that. And finally, also, the development of AsterX is also all public, and you can even check out the Git repository. So let me try to see if I can open this. So as you might see, so this is the GitHub repository for AsterX, and you have all these different modules that I talked about. And then there is some information about a little bit of an overview, what are the available modules, what functionality they provide, then how to get started with, how to download, how to compile, and there's some sample Jupyter notebooks and plotting scripts, and then links to other useful repositories like CarpetX, SpacetimeX, and things like that, and code papers as well that for AsterX, as well as the subcycling paper that based on the subcycling algorithm that has been implemented by Li Weijie et al., and then some other related tutorials and previous talks. So in case you're interested to check this out. Let me go back to my slides. Right. So once we implemented AsterX, we had to do some verification, validation of our code in terms of how it performs and if it actually reproduces results what's been in literature. So here, for instance, we started with the shock tube tests, and this is the Balsara test suite that we performed from and Balsara 1 to 5, and they all and these are the final time profiles for density on the right and the y component of the magnetic field on the density on the left and y component of the magnetic field on the right, and they seem to agree quite well with the exact solutions. Next, we perform some two-dimensional tests, for example, cylindrical explosion on the left and magnetic rotor on the right. And these profiles also quite match, the final time profiles match very well with what's been shown in the literature. For the magnetic rotor test, we also included an additional box here, like an AMR box. So the shock was able to pass through this AMR level as well, and we don't see any issues in this case. Another test we performed was this magnetic loop direction. This is something that is also included in the notebooks later that you can also try. And on the right is this Kelvin-Helmholtz instability test. So here, what we did was we played around with this adaptive block structure mesh refinement. So it is dynamically refining and de-refining. And as you might see towards the end of the simulation, as these curls are formed in density, there is some refinement happening close to the curls. So let me go back here again to this plot where you can see actually there was some, the code was trying to refine around regions where there were shocks or the curls were forming. Next, to include also gravity, we performed some single neutron star tests. We also evolved along with space-time. So the test I talked about earlier was all in Minkowski space or flat space, while here this is also evolving with space-time. So here on the left, we used, for example, the CanudaX code and performed the TOV star simulation. While on the right is it's the rotating neutron star, and the initial data was provided through this COCOL ID, which has been an importer that has been provided by Maxwell Rizzo, Antonio Socaris, Roland Haas et al. At UIUC. We did some convergence tests. So on the left, you see the evolution of rest mass density with time, and for 3 different resolutions that we adopted for this TOV simulation. And as you would see that as you increase the resolution from blue to going to red, you dissipate much less in this, and also the amplitude of the oscillations also decrease, so which is a good sign showing that the code is converging. Of course, if you go to infinite resolution, you would expect a straight, a flat line. So that's essentially still the idea. And when you do, once you take the fast Fourier transform of this, you actually can see that there are these oscillation modes that are present in this TOV star, and you can compare it with a perturbative code, and which are provided, and these perturbations, the oscillation frequencies are provided by this perturbation code, and you can check if your solution is actually matching with that or not. And that's what we did here. So when you go to really high resolution, and these perturbative codes gave these oscillation frequencies, which are showed in these vertical dotted lines, and the AsterX results are in these solid lines. So we see that our peak frequencies are matching with what's been provided by the one in literature, by the perturbative code. Next, we also started looking into performing these magnetized accretion disks around black holes, which are called these fishbone Moncrief disks. And this is a work led by Mikhail Chabana from RIT. And here we see that there's about when you evolve the system for a while, this is like about 3000 M later, you can see density on the left, the z component of the velocity in the center, and the z component of the magnetic field on the right. You see that there are these strong jets that are formed, and these are magnetically driven. Similarly, we started also looking into performing binary neutron star mergers with AsterX, and using the initial data from Fuka. This is imported provided by Samuel Tudor. For instance, in this simulation, we evolved this with idle gas. And here we were probing the prompt collapse case, where you have the merger of the two neutron stars, and then the the remnant is directly a black hole that forms within a second or so. Whereas we also explored the long-lived remnant case where you have the merger leading to a metastable neutron star that survives much longer and not does not collapse. So this is about say 52 milliseconds after merger. And finally, we also we have, like I mentioned, support for tabulated equations of state. So here what you see is the evolution of density on top left, x, y, and xz planes. On the right is the evolution of temperature on x, y, and xz planes. And on bottom left is evolution of magnetic field on x, y, and xz planes. And this is again evolved with what an APR4 equation of state. And this was the table provided by uh, RIT student Alan Wen. And as you see, as the merger happens, you form. There's a dynamical ejecta that comes out right after merger, and then you form, in this case, also a metastable uh, neutron star remnant. And as soon as this forms, a few milliseconds later, you start to develop this what we well-known instability called the M1 instability, and that develops these waves, the spiral waves in the disk. And can be seen much more prominently in the temperature as well. This is like a flower-like pattern if you look at a rose from the top view. So that's and it's still this is all work in progress, and we are trying to now evolve a different equation of state as well. Another application for AsterX right now is also for modeling gas evolution around supermassive binary black hole mergers. So this is again the work led by mainly by the RIT group. And in this case, what we try to do is we equilibrate a circumbinary disk in a code called spherical NR. This was the simulation done by Lorenzo Nocci. And then we take this information from the spherical grid and we then hand it off to AsterX. And the initial data for AsterX is what you see on the right. So there is a cutout in the spherical grid where on the right side you actually then have the black holes on the grid itself. And then we started to evolve this system with AsterX, and you see that once the streams that are then kind of starting to being formed around the two black holes, and which will eventually form mini disks around these two black holes. Essentially, these are again very promising LISA sources for gravitational waves, and we are also here with AsterX, we're trying to model the electromagnetic counterparts in terms of mini disks, accretion, jets, and etc. Another ongoing development in AsterX is the inclusion of higher order methods. So we already had implemented the reconstruction, the Vino-Z reconstruction that I mentioned earlier, and also added. So this reconstruction is like a fifth order, can go up to fifth order accuracy, but then you also need to add flux corrections in order for the whole high resolution shock capturing method to be fully higher order. So we added these flux corrections as well, and then there was again Alan Wen from RIT took over this project, and he also added more wider stencils to compute staggered B from the curl of A, and now we also have a higher order for the evolution of B as well. So the ongoing tests include this Alphen wave test. So on the left, what you see is the convergence test for this Alphen wave, which is simply a wave that advex through your domain and without any shocks. And once you compare the initial and final time results for example, here in this case is the y component of B, and what's shown here is the L2 norm. And these are these results for the simulations with different resolution. As you see that once you have just the standard, no higher order correction involved, you get only second order accuracy in the simulation. Whereas once you go to higher orders, even sixth order, the green line essentially is showing the sixth order accuracy, and this is what we can also get in this test. Whereas on the right side, there's just still work in progress. Alan is now evolving TOV stars with these high order methods and seeing what results we can get with that. Another important ingredients in such simulations are neutrinos, specifically if you're trying to model binary neutron star or doing BNH and black hole neutron star mergers, and you want to accurately model R process nucleosynthesis, all the and also model matter outflows and winds. Neutrinos can have an important impact. And of course, when you're trying to model coarse collapse supernovae, as well as, like, say, disks of collapsars, neutrino definitely play an important role in that. So, to that, to include neutrinos, there has been a multi-institutional effort to add what we call as the guided moments approach. So some of us are working what is called as NUX-M1, which is a moment-based neutrino transport module. And this is essentially a port from the THC M1 code of David Latiche et al. And this has already been ported and now has been coupled to AsterX. And for the microphysics, essentially, which provides the neutrino matter interactions, there are different libraries available in the market. So we've coupled that with this code with one available from Chiesa et al., which is called BNS new rates. And this work is also all publicly available. And this is again a multi-institutional effort, including me, Alan from RIT, and others from UIUC, and of course everyone else as well. And on the other side, Li Weiji et al. Have been working on this Monte Carlo-based neutrino transport module, which is essentially considering neutrinos as particles. And Li Wei has then coupled this code to a microphysics library called vclip, and this is also again all currently in development and all available on GitHub. And the main goal is to actually couple both these codes together to develop what is called as this guided moment scheme, which has been introduced by Izquierdo et al. And this would both of these codes independently have their own drawbacks. I don't want to go into the detail of that, but happy to talk about it later. But when you couple these codes, you can get much more accurate neutrino transport, and that's the main idea here. Next, we also we did some benchmarking for AsterX. So we did some scaling tests, and for example, on the frontier cluster, and for instance, in this case, we adopted 3 different setups for TOV. We involved a TOV neutron, TOV star, and setup A was just in cowling, so not evolving the spacetime, plus in the uniform grid. Setup B was we evolved spacetime using the Z4C module, and again in the uniform grid. And setup C contained also 8 levels of AMR. And on the right, I show some results for strong scaling, going from say a couple of GPUs to 8,000 GPUs, and we saw that we are able to scale not that well, but decently well, up to 8,000 GPUs is like about 20% performance. Of course, GPUs are strong. GPUs are not made for strong scaling because you want to have as much compute load as possible. You want to saturate the GPU. So as you reduce the compute load, is what you actually see what's been shown in the plot. Of course, the performance, you're not actually using the GPU really well, and hence the performance, the strong scaling doesn't work that well on GPUs. But well, on the when you do the weak scaling, in this case, for the same 3 setups, we saw that we can get up to 70 to 80% weak scaling, going up to say 16,000 GPUs, when compared to like a few GPUs in performance. There was also a talk on subcycling by Li Wei. So when we included subcycling with coupled subcycling with AsterX, we also saw that there was, with subcycling, the performance gain was by at least a factor of 3 to 5. So subcycling really makes our simulation faster. Lastly, we also try to profile our code to see if you're actually using the GPUs well, if there is a lot of memory transfer or not. So we use something called as this NVIDIA Insight systems. And here what you see is a simulation that was run for a few iterations. So each of these blocks, this essentially, as if you can see my pointer, this essentially is one time step. And we also looked at if there is here in the black is this, what it's shown here is a CPU workload, and on the blue is the GPU workload, and in the red is the memory transfer. So when we are actually evolving or running the code, we see that there is not much memory transfer and everything is only running on the GPUs, and that's exactly what we want. We want to run our kernels, GPU kernels, on the GPUs and avoid any memory transfer. So this was a positive outtake. And then we've also used another profiling toolkit, which is called the HPC toolkit. And this is essentially to see which schedule functions are being the bottleneck in our code, or how we can make our code faster. So for instance, in this case, we saw that, okay, the fluxes computation seemed to be the most expensive. And this is expected because when you're doing computing the fluxes, you're doing the computation on the cell faces on all three different directions. So that is something that we identified, and we're always trying to optimize as well. And this brings me to the end of the slides. If there are any questions, I'll be happy to take them now.
Thank you very much, Jay, for a very nice talk. Is there any questions?
Yeah.
I can see any questions in the chat or raised hands. If you have any questions, please raise your hands or type it in the chat so I can read it.
If you want, we can also take a 5-minute break, and we can switch to the notebooks and maybe try to run 1 or 2 simulations with AsterX.
Yes, that would be perfect. That would be perfect. Yes. Perfect. Yeah.
All right, thank you. So this is for the second part. We will try to maybe run a simulation or two using AsterX. And again, I thank Steve for helping me set up these tutorial notebooks. So the first notebook that we can check, so there are a number of notebooks that you might see on the screen with AsterX. So the first notebook we can check out what is called this AsterX primitive commented, and this is a notebook that one of my colleagues worked on. Example that we can look through, but I think most of the content has been covered past by Steve, Roland, and Eric. But what is essentially here is a comparison between a CarpetX about mentioned earlier, we are trying to solve a GRMHD equation. So what is a simple equation is the evolution of the densities. Uh, I'm sorry.
Please continue.
Right. So I just kept this note on the list so that participants could what we use in CarpetX, for example. And for instance, the kind of header file you need to what kind of how to declare your scheduled function, and you need to include this CTK argument X, for example, for the carpet version. Then there are the different things, when you're trying to loop on the GPU, there are different things you need to take into account depending on you are looping over, if it's like these are cell-centered variables or vertex-centered. There are different syntaxes for that. And all of this information is here. I don't go into in deep. I think this was already covered in the past. So let me jump directly to one of the notebooks that we can try and run. So I'll start with this Balchara shock tube test. So again, this is just generically it's a shock tube that you're trying to evolve. And for the test setup, you define some left hand side states for the primitive variables. Example, density is 1, the velocities initially are 0, pressure is 1, and then you have the right state where you have a lower density and lower pressure. So what's going to happen is you have more highly dense and higher pressure on the left, and you have lower density pressure material on the right. So the shock will then traverse towards evolution, it will start going to the right. And of course, it's not straightforward, and that's what we need simulations for to see what exactly happens. Then you also have some, these are also magnetized shocks. So you have some prescription for what kind of magnetic field you impose on the state. And we will use ideal gas equation of state with gamma equals 2. And all this initial data is fed by this thorn called seeds. And this grid domain and the shock will be on the right direction, and we have about 200 volts. Okay, so let me just continue. So this is essentially, trying to evolve a shock tube. So you can already start to execute these cells. First, we can move to the cactus folder.
Jay, your screen is gone for me.
And so let me try to.
Yeah.
Thank you for being patient about this.
Don't worry, Jay, we will finally get that information from you.
Yes. I mean, you can, of course, run the notebook in the background. I'll just try to explain what the parameter files mean. So here we have the parameter file, and these are the different thorns we will use for the simulation. For example, some of the AsterX related thorns are included here. Then the number of levels is set up here, and this is a uniform grid simulation. We will use refinement level. This helps to set the domain size, and here you also set boundary conditions. Next important thing is the number of cells. So along X we have 200 cells, while on Y and Z we have just 2. So this is again more or less the shock will traverse only the direction. And we use again astroseeds for defining what.
Again, your screen gone.
Hi, are you still there?
Yes, Jay. But your screen is gone for me. Yeah. Let me ask the question in the chat before you continue. Omar asks, what kind of equation of state and initial magnetic field can be fed into AsterX, can be modeled in AsterX? I just okay.
Oh, that's a good question. So with AsterX, you can use both all the three kinds: analytical equation of state, like an ideal gas equation of state, or a barotropic equation of state, like a polytropic equation of state, as well as you can use this tabulated equation of state, which is pressure as a function of rho, temperature, and y. And this is all provided through this equation of state EOSX module. All right, I will try hard to finish this as quickly as possible. So yeah, you can, this is the parameter file that we will use. Some of this also shows some details on what kind of reconstruction scheme we will use, what kind of flux solver. For example, here it's HLLE. Reconstruction scheme is VNOC, and then these are different parameters for the contour prim. So the first contour prim is the noble contour prim that I talked about earlier. And then if the noble fails, there is a backup contour prim like the Ponzuela one. And the equation of state we will use is the ideal gas, which is using gamma equals to 2. And here are some of the ways of also outputting what we would want to, the data that we want to output using either the TSV format or also the OpenPMD format. And there is some also time and report information if that one can set in the power file. Next, let's try to run the simulation. So this is done through the SimFactory we talked about earlier. And once you submit the job, you should be able to follow through how if once the simulation starts through the show output command. So I'm not sure if the nodes are actually free, so I think it probably will take some time for this to evolve and the simulation to start. I don't know if participants are able to follow through and able to run this simulation already. So at least for me, it has started. So you might see some out already. You see the serial of the simulation is printed here. And next, you also see some evolution. So you will see some information of the simulation time, number of iterations, things like that. So once the simulation finishes, probably going to take about 5 minutes or so. We can then move on to visualize this simulation data. And for this, either for visualization, we have support for either silo formats as well as which can be used for visualizing through tools like Visit, and then also OpenPMD formats, which then we can use to which can then be used for visualize using Python. So in this notebook, we will try to use the OpenPMD format, and we have some more information below on how to use Python to visualize the OpenPMD data. So meanwhile, there are also information about Silo. So I've included links on Silo as well as OpenPMD here, in case people are interested to look into what these data formats entail. Now, I think my simulation is still running in the background. So here you can also report information. For example, most of the time is taken by this ODE solver. And then, as I mentioned, the fluxes is the one that takes most of the time in AsterX, followed by here in this case is contour prim, and then there's this our computation of RHS and right-hand size is not as expensive as for example fluxes. Let me see if I anything on. Meanwhile, if there are any questions, I'll be happy to take them. As I hope if let me know if there are people who are not able to run the notebook or if they find any issues.
Yeah, Hodek already finished. Congratulations. And is there any question that you would like to ask? Please type it in the chat or unmute yourself and ask. I don't see any, Jay.
Okay.
You may
Maybe
continue
give me
if
2
you
more
like.
minutes. I think my simulation is,
Yeah.
my simulation is like halfway done.
Yeah.
Once it's, I think, fully done, maybe I can go towards the visualization part.
Yes.
So meanwhile, you also see that CarpetX prints out these some information about your simulation and this and the standard output. For example, it tells you the simulation time, how many iterations per second your simulation is doing, what is the simulation time per second, number of grid cells you have one, and then how many grid cells updates per second are happening. Then some information on performance in terms of what's the total evolution time. So it's less than 5 minutes for now. And out of that total evolution time, how much time is for computing and how much time is for outputting as well, and number of iterations involved, average iterations per second, and all of that. So I think this can also give some hints on how good or bad your code is performing, and for different grid setups. And yep.
Thanks, Jay. Any questions to fill the time?
Other people who already finished running the simulation?
Hodek
Or
is finished.
is everyone?
Just one person, I saw.
Oh, most of them have finished? I see.
Yeah.
Yes, it seems quite lightly loaded. So if anybody else wants to run it, there's plenty of processing power.
Yeah, it's
Oh,
time to
wonderful.
run now. Yeah, it's time to run now.
Or if you're also
we've now got a
finished.
few people running, so yeah.
Perfect.
Okay. So if more people want to try other notebooks, you can already try a TOV for installation. So you can check that notebook out meanwhile as well if
Yes, just run and crash the server again, as you did in Monday.
Well, I think it's unlikely to see a repeat of Monday. See, the basic problem that the server has is the disk access speed. And with everybody untarring a gigantic file at once, that just hammers the disk like nothing else. But since people have already got their codes unpacked, there shouldn't be any more problems, unless 50 people log in or something. I'm not sure what the exact number would be, but we should be good.
Yes. Thank you, Steve.
Okay, maybe I can already talk a little bit of visualization while my simulation still runs. So as I mentioned, there are different formats, Silo and OpenPMD. Here in this case, we will try to use the OpenPMD to visualize using Python. Now, once in the OpenPMD data, you have what we call a series, which is a collection of iterations, and each of these iterations will conduct record, and then which will have information also on structured data like the meshes, or can contain unstructured data like particles. For now, AsterX only outputs the mesh data, and each of these records will have one or more components. And if, for example, if a record is representing a scalar field like density, for example, it will have just one component. But if in case you have a vector field, like for example, magnetic field, you have or velocity, then you would have three components. And since I'm waiting for the simulation to finish, I might not be able to load this. Until then, I can. This is like, for example, generic kind of what you might see once you execute these cells of what kind of iterations you have and what records you have and what data you have in these files. But you once you have loaded this the C.
Your share screen is gone again, Jay.
Hi, I hope this is the final time it happens. Fingers crossed.
Yes.
Sorry about that.
No problem.
So I want to mention that my simulation is still running. It's not done yet. And I was trying to do, so I think it's 75% done. So let me see once it stops. So I was trying to describe about the data that we have through OpenPMD. And here, as I was mentioning, you can, for different iterations, you have records, and each of these records will have it could be either one, if it's a scalar field, or it can have three components if it's a vector field, for example. And here is how you can start to define a dictionary, and then you can load all of your iterations. In first, you have to allocate this empty dictionary, and then you can load all of these iterations within this dictionary, and then finally you can register all of these. You can flush all of these data chunks into as valid NumPy arrays, and using this command. And lastly, like I mentioned, we can then use Python to plot the results. So you would have to load the record that you want to visualize. In this case, it's hydrobase x underscore row underscore patch 00, which is the patch you're on, and then also the level 00. And then the component that you want to visualize would be hydrobase x underscore row. And similarly, you can also visualize other data forms that you have saved in the par file. And rest more or less is trying to access this 3D the dictionary that we initially defined, and trying to access these different iterations, record, and components. And you load this into a 3D array. And finally, if you want 2D plots, you slice, say for example, along the axis, and to get an XZ2D image. So let's see if my simulation is still. Right, it has reached up to 0.33. So ideally, I should already have some data that I can try to visualize, even if my simulation doesn't go to final time. So let me try and see if I can actually do that. Pause the current curve and see if I have already some data that will try to visualize. All right, so maybe we still have some data to check. So let me try to execute all of these cells. And we will use this to actually make a movie. And we also import OpenPMD so that we can load the OpenPMD data. This is just for inlining. Now this is like reading the series, OpenPMD series, and with this cell. Ooh. Okay. Let me see if I can still run this. Okay. Like I mentioned earlier, once you load this data, you can see how many iterations you have, what are the different components for the different records, and what are these different components for each record. So for example, for magnetic field, you have the X, Y, and Z component of BWEC, whereas all the scalar data, like example, epsilon or density, you have just one component. Once you flush this and try to visualize, finally, hopefully, we can move out of this as well. And there you go. So you have this shock propagating, and how this is how the density changes in time. That was this
Jay,
was a just like a. Mhm.
you're saying this is how the density changes in time, but I don't see a plot on the shared screen currently. I'm wondering if we've got a delay again or oh, there it is. Okay.
Oh shoot! Let me try to share my screen again. Yeah, are you able
It
to
just
see my
updated.
screen? Sorry.
Yeah, I think it's just
Oh, okay, my
delayed.
bad.
We
Okay.
can.
Yeah, so this is, for example, for density. You can for the brevity of time, you can play the same game for these two different notebooks that we have for. There's a 2D test called the loop advection, and there is also a TOV, magnetized TOV style that you can visualize. But yeah, I probably, if there is interest, but I would probably stop here for now, and I'm happy to take any questions. And I sincerely apologize for my internet issues. Sorry about that. I didn't anticipate that.
No, but
Thank you.
thank you very much for your very informative talk and tutorial, Jay. Thank you very much. Now we will have questions if there are any.